welcome to the CSE Colloquium. Today's speaker is Sanjam Garg. Sanjam did his PhD at UCLA with the Mitzahai and Raviv Ostrovsky, and he's did some amazing work in his PhD thesis on the first good candidates for multilinear cryptography, and also work on obfuscation of software, and he's currently a postdoctoral fellow at IBM TJ Watson. It's great to have Sanjam here.
Thanks for the invitation. I'm really thrilled to be here. And as mentioned, I'm a cryptographer, and I've seen that whenever anybody talks about cryptography, the kinds of problems that come to mind are things like data encryption or digital signatures. And indeed, cryptographers have done an excellent job at providing fabulous solutions to these problems. But then there's this problem of software obfuscation, for which cryptography has traditionally been seen as completely irrelevant. And for good reason. So far, we didn't have any real solutions for this problem. Today, I'm going to talk about this very problem and tell you about our recent results, which sort of provide the first theoretically sound, general-purpose software obfuscation solution. So let's see what obfuscation is all about. The goal of obfuscation is to make computer programs unintelligible, but without affecting their functionality. So consider, for example, we have a party, Alice, and she has a program P, say in our favorite programming language, and she wants to give this program to Bob, but only in an obfuscated form. Okay? Alice wants Bob to be able to execute this obfuscated program, O of P, on his computer just as he could have executed the original program P, but Alice wants this obfuscated version to be unintelligible for Bob. In other words, if the original program P had certain secrets that were embedded inside it, then Alice wants the obfuscated version or the scrambled version to hide these secrets. Okay? Defining what does it mean for the obfuscated version to be unintelligible, or what are the kinds of secrets inside programs that we're trying to hide, turns out to be rather tricky to define formally. But I still want to give you some idea about what it means, and I'm going to do that with an example, and in fact an application of obfuscation for the task of converting any private key encryption scheme to a public key one. So this application actually has really cool history. Let me tell you a little about it. So this application was actually first suggested by Diffie and Hellman in 1976. At that time, we didn't know how to do obfuscation, and in fact, we didn't even know how to do public key encryption. What Diffie and Hellman suggested was, well, if somehow we had access to obfuscation, then this would allow us to construct first candidate for public key encryption. We all know that public key encryption was then later realized by RSA, but the goal of realizing obfuscation has so far remained elusive. So let's see what this application is, and hopefully it'll give you an idea about what are the kinds of secrets that we're trying to hide inside programs. In a private key encryption scheme, it's a private key that enables both the tasks of encryption as well as decryption. So given the private key, you could encrypt the plain text to obtain the corresponding ciphertext, which could then be decrypted using the same private key to recover the original plain text back. Okay? On the other hand, in a public key encryption scheme, it's a public key that's made available to everybody in the world that enables the task of encryption, and a corresponding private key that then allows ciphertext that are being generated using that public key to be decrypted. What Diffie and Hellman suggested was that if I was to take the encryption procedure of a private key encryption scheme with the private key embedded there and obfuscate this procedure and publish the obfuscated encryption procedure as my public key, then this allows for a generic way for transforming any private key encryption scheme to a public key one. Note here that the obfuscation or the obfuscated encryption procedure there is attempting to hide the secret key that's embedded inside this program. Okay? So this hopefully gives you an idea about what is the goal of obfuscation, what are the kinds of secrets that we're trying to hide inside programs. As you can imagine, obfuscation, or this tool, seems to be really powerful and has the potential for lots of applications. I want to start by talking about an application of obfuscation for the problem of patching software securely, something that's typically not considered in the domain of cryptography. Okay? So imagine a security software such as Norton that you have installed on your computer, and let's say one fine day, there's this really hardworking team of security engineers at Norton finds a bug in the software. Now, they work hard again to release a patch to fix this bug. Now the problem is that an attacker who has access to this newly released patch could sort of figure out what is the bug that this patch is trying to prevent, and given this patch, figure out what the bug in the original piece of code was. We all know that nobody wants to apply patches or wants to postpone it as much as they can. So it certainly takes a few days and potentially even few weeks in many settings for actual software patches to be deployed. And now what this does is it puts the machines that have not been patched at risk from attackers who have access to this newly released patch and have figured out what the bug in the software is. This actually turns out to be a real security problem in how software patches are applied currently. And obfuscation offers a really natural solution to the problem. The idea being that if Norton was to release this patch instead of in the clear form, in an obfuscated form, then this prevents an attacker from figuring out what the bug in the original piece of code was, and thereby preventing attacks. Of course, once large-scale deployment of this obfuscated patch has happened, in a month or so, Norton could then replace a more efficient version of this patch, moving to an overall more efficient system. Okay. So this is an application of obfuscation for a problem for which cryptography is seen as completely irrelevant. So this is something really cool. But if you wanted to do something like that, or achieve obfuscation in general, then there are sort of two ways around it so far. So the first is for you to actually sit down and scramble your code to the extent you can, and make it really hard to figure out how this program works. The code that you see here is actually a winning entry from the International C Code Obfuscation Contest. There's a contest by that name. And what this program does is that it calculates the square root of the number that's given to it as input. But let me assure you that if you were to sit down and stare at it for a couple of hours, you don't have to actually depend on this comment that the author has written left in the shape of a square root to figure out how this program works, but you can figure out everything about this program. Okay? A slightly more sophisticated way would be for you to go online and buy one of these software obfuscation tools, such as the Crypto Obfuscator or the Enigma Protector. These tools have fancy names, but have nothing to do with cryptography. And how they work is by changing function names, changing variable names, adding dummy code to the program. Though these techniques are going to make the task of sort of figuring out secrets inside programs harder, they're not going to be able to hide them in sort of a secure way or a cryptographically secure way. Specifically, if you were to go back to the example of using obfuscation to convert a private key encryption scheme to a public key one, there's no way either of these techniques are going to help you hide private key inside a program. Okay? So in summary, these tools make the task of reverse engineering time-consuming, but certainly not impossible. Okay? So this is something that's completely unacceptable for us cryptographers. We like to have rigorous security notions and then constructions realizing those notions or achieving those notions. But if you were interested in cryptographically secure obfuscation, then you would be limited to extremely simple classes of functions. Okay? Let me give you a representative example of the kinds of functions or programs that we knew how to obfuscate prior to our work. So this function is something that we call, or was previously called, point function or the password checker function. It's an extremely simple function. It's parameterized by a password and a secret message M. And takes as input a string X, checks if it's the valid password, outputs a secret message M if it indeed is the case, and bottom otherwise. So this is an extremely simple function. And what in principle it is achieving is that if I give you an obfuscation of this function or a program that implements this function, then either you know the password, in which case you should be able to figure out this secret message M, or if you don't know the password, then both the password and the message M should continue to remain hidden from you even after I gave you this obfuscated program. So this is absolutely a very simple function and certainly a very far cry from the goal of obfuscating all programs. And in fact, there's been a strong evidence towards the kinds of obstacles that lie in constructing or realizing obfuscation for all programs. This has changed with our recent results, which sort of, for the first time, provide a first rigorous or theoretically sound construction for software obfuscation. This has been possible using a new mathematical tool called multilinear maps that were also realized in another recent work of mine. One point I want to mention is that the construction that we have are prohibitively inefficient, and they're not ready for practical use. Everything is polynomial time. They're just large polynomials. A subtle point I want to make is that prior to our work, we didn't even have any secure heuristics for this problem. So what I mean by that is that for every solution that has been conceived or put forth in the literature, we knew of precise attacks against those constructions. So every solution that was out there, we knew how to actually attack and break them. And subsequent to work, there have been a number of long-standing open problems in cryptography that have been solved using obfuscation and multilinear maps. Let me tell you about a few of them. The first open problem I want to talk about is in the context of non-interactive key agreement. So this problem has actually been solved for the two-party setting. Let me start by talking about it in the two-party setting. So the problem is that we have two parties, Alice and Bob, with public keys pKa and pKb respectively, and secret keys ska and skb respectively. Okay? And what they want to do is they want to use their own secret key and the other party's public key to compute a shared secret key kab. So in particular, Alice wants to be able to use her secret key ska and Bob's public key pkb to compute this value or shared secret value kab. And similarly, Bob wants to be able to use his secret key skb along with Alice's public key pka to compute the same value kab. And sort of the security guarantee that we want is that an attacker who has access to just the two public keys shouldn't be able to figure out anything about the shared key kab. So this is a very simple and a natural problem. It was first posed by the original paper of Diffie and Hellman, the paper that laid the foundations for modern cryptography as we know now. It posed this problem and gave a solution for the two-party setting. Okay? However, this took us roughly 24 years to solve this problem for the three-party setting. Gödel, in his Jew in his Gödel Prize-winning paper, developed or introduced this new mathematical tool called bilinear maps that enabled him to give a solution for the three-party setting. However, the problem for 4 or more parties was still left open. Okay? So the tool multilinear maps that has helped help in enabling obfuscation has also helped solve this problem for 4 or more parties. You can do it for arbitrary polynomial number of parties. Okay? So the tool that we're using is actually, bilinear maps was the tool that Jew had used. We're using the same concept, but different underlying mathematical objects. So it's the same concept, but he was fundamentally restricted to 3 parties because he was using elliptic curve cryptography. And what enabled us is that we could extend his tools with ideal lattices and break that barrier and get the solution. Subsequent to this work, there have been a number of works. For example, the first one is by a team from Stanford, another one follow-up work of mine jointly with them, where we improve on the constructions in terms of efficiency and various other parameters. The second open problem I want to talk about is functional encryption. We all know that probably NSA is reading our email, and many of us may not be as happy about it. A simple solution out there is, well, if Alice here, for example, doesn't want NSA to read our emails, you could publish her public key so that anybody who wants to send our email could encrypt the email that they want to send with the public key so that Alice, who holds the secret key, and she alone can decrypt those emails. But now the problem with this solution is that if Alice keeps her email on the cloud, for example, if she uses Gmail, then she doesn't want to give up on the conveniences of the cloud. Specifically, in the case where she's using Gmail, she would still like Google to be able to figure out which of our email are spam without having access to read its email. Well, one way for Alice to do that is just to give her secret key to Google so that Google could decrypt the email and check if they're spam. But then that sort of defeats the entire purpose of having the email encrypted and trying to prevent NSA from reading them. So now that this is a highly non-trivial problem, Alice wants, let's say Alice gets an email from a Nigerian prince, then Alice wants Google to figure out whether the email is coming from a fake Nigerian prince, and is spam, or is actually coming from a real Nigerian prince who also happens to be a friend of Alice. And while doing this, Google shouldn't even learn the fact that the email is coming from a Nigerian prince. Okay? So it's a very non-trivial problem, but obfuscation sort of makes it completely trivial. Think about the following program. Takes the encrypted email as input. It has the secret key embedded in it. So the program decrypts the encrypted email that's given to it as an input, checks if it's spam or not, outputs yes or no. Alice can just give an obfuscation of this program to Google, enabling it to check which of the emails are spam, but not learn anything else about them. And the goal here for the obfuscation is to hide the secret key that's embedded inside this program. And similarly, Alice could give out multiple such obfuscated programs or specialized secret keys enabling different tasks. For example, she could give out a specialized secret key. She's a professor at a university that enables the department secretary to read emails that pertain to the topic of graduate hiring. So, and she could give an unbounded number of such secret keys. So prior to our work, we knew how to realize this primitive, but we were extremely limited in the kinds of functions for which secret keys could be given out. Specifically, we knew how to realize functional encryption for where secret keys were given out corresponding to functions as simple as inner product. And the solution that I just described to you using obfuscation gives immediately a solution for arbitrary functions. Okay? Subsequent to this work, there have been a number of follow-up works. For example, the first two here, the first one is by a team from UCLA and MIT, and the second one by a team from Washington, D.C. area. They look at a setting where you have secret keys which look at multiple emails at the same time instead of just looking at one email. There are certain subtle issues that arise in that case. The final open problem that I want to talk about, is the personal favorite of mine, is witness encryption. So typically, whenever we think about encryption, we're always thinking about encrypting to a specific recipient. We'd like to rethink that. We don't want to encrypt to a specific recipient, but we want to encrypt to sort of an arbitrary NP statement. So we have an encryptor, and he has a message M, and he wants to encrypt to an arbitrary NP statement X. Think of as a SAT formula that you have in mind. And she doesn't have a recipient in mind. So she generates the ciphertext. She still doesn't have a recipient in mind. She just generated the ciphertext. And the claim that we want is that if a receiver, potentially even 100 years later, comes along and says, look, here, I have a satisfying assignment for the SAT formula, or more generally, a solution to the NP statement or witness for the NP statement, then that witness or that satisfying assignment should enable decryption from the ciphertext and recovery of the original message M. So this tool has really cool application. Let me tell you about one. It'll give you an idea of why I'm so fascinated by it. Think about your favorite problem in mathematics or computer science. Let's say twin prime conjecture, and let's say you're really fascinated by it. The problem says that there's an infinite family of twin primes, where twin prime is two primes separated just by 1, 11, 13, 17, 19, and so on. So the conjecture states that there's an infinite family of such primes, pairs. And let's say you're fascinated by it, and you want to leave $1 million to anybody who solves this problem. Witness encryption provides sort of a solution to this problem, where you can put the $1 million in a safe and encrypt the combination that opens the safe to the twin prime conjecture. Okay? So anybody who, potentially 100 years later or 1,000 years later has access to a satisfying or solution to the twin prime conjecture. He says, look, here I have a proof for the twin prime conjecture. Then that proof should enable decryption and recovery of the combination for the safe and the $1 million. So something really cool about this primitive is at the time of encryption, the encryptor doesn't even know whether the statement that he's encrypting to has a solution or not. Okay? So at the time of encryption, I don't know whether the SAT formula has a satisfying assignment or not. I don't know whether the twin prime conjecture is true or not. And if it does, there could be an exponential number of them, and each one of them should enable decryption. So this problem was actually first posed by Rudik in 1989, and so far we had no idea if something like this could be realized, and obfuscation sort of offers a really simple solution to the problem. I'm not going to tell it, but you can sort of imagine it on your own. Subsequent to this work, there have been a number of follow-up works. One point I want to mention was that sort of the solution given obfuscation is pretty simple, but actually was developed before we had obfuscation. Sort of the techniques that were used there were sort of a stepping stone towards realizing general purpose obfuscation. So there are many other open problems that obfuscation has helped resolve. I won't have time to talk about all of them, but I quickly wanted to mention the names. So if any of these sound interesting, then I'll be happy to talk about it offline or in one-to-one conversations. So I just wanted to mention the name. They may not all make sense, but just to mention the names. So obfuscation has been useful in realizing multi-party computation with optimal communication, constructing new broadcast encryption, traitor tracing schemes, new deniable encryption schemes, removing random oracles from cryptographic constructions, new separation results for circular secure encryption schemes, functional witness encryption scheme, new impossibility results in cryptography, and new zero-knowledge protocols with fancier properties. So just to give you an idea, just in the past 1 year subsequent to work, 50-plus papers have been published using the techniques that we've developed. OK, so hopefully I've convinced you that obfuscation is interesting and we should care enough about it. Let me move on to sort of the technical part of the talk, where I want to give you some idea about how we actually do obfuscation. The actual construction for obfuscating arbitrary programs turn out to be rather complicated, and I'm not going to do that, but I still want to give you some idea. I'm going to do that by giving the obfuscation methodology for a special program or a special function. In fact, the witness encryption problem that I was talking about. And this is the specific techniques that I'm going to talk about were developed in a joint work with Craig Gentry, Amit Sai, and Brent Waters. And for this part of the talk, please feel free to interrupt me, ask questions. I'll welcome questions for this part. OK, so before I tell you the special function that I want to obfuscate, or what is the specific function or the program that we're trying to obfuscate, I want to start by some high-level principle or the high-level idea about how obfuscation is done. These are going to be fuzzy, but I want you to keep them in mind, and then we'll see how these ideas become applicable when I will talk about the specific function. So these are going to be like fuzzy ideas, but keep them in mind. So when you think about sort of your arbitrary C program, you have sort of a machine code, and you run step by step. For the obfuscated version, we're going to have a bunch of, we're going to take this program and compile it into a bunch of encrypted jigsaw puzzle pieces. So these are a lot of the pieces that you see here are lots of different encrypted jigsaw puzzle pieces. What that means will become clear later on, but just that's what we're going to compile it to. And how computation is going to proceed is that for every input on which you might have wanted to execute the original program, there'll exist a subset of the jigsaw puzzle pieces which, when put together, reveal the output of the program on that input. Okay? So for every input, there'll exist a subset there. You can put them together, and those pieces will fit together, and you'll learn the output. And the security will arise from the fact that no other combination fits. Okay? So for every input, there's a legitimate combination, but there are other illegitimate combinations which don't correspond to any input. Or there might be subsets or partial combinations of legitimate combinations. We're going to claim that none of those pieces will fit together and reveal anything. They're just going to be random ciphertext. This transformation is sort of going to be done in 2 steps. In the first step, we're going to take the program and convert it into a bunch of unencrypted jigsaw puzzle pieces, which will then be encrypted using this new encryption scheme, or what we call multilinear maps. This new encryption scheme will enable that if you took the right pieces, then they somehow magically fit together. But if you took any illegitimate combination, they will not fit together. So this is something that will be guaranteed by this new encryption scheme or multilinear maps that we have developed. Okay? So as I said, these ideas are going to be fuzzy. Just keep them in mind. Let's get very concrete now. I'm going to tell you the exact function I want to obfuscate, and then we will see how these ideas are applicable there. Okay? So the function that I want to obfuscate is this function f. It's parameterized by 2 quantities, a public graph G. So it's parameterized by this public graph G and a secret bit B. So the public graph G is a bipartite graph, and it's shown in blue because it's public, and the bit B is secret, so it's shown in red. What this function does is that it takes as input a string T. It checks if the string T describes an exact cover in the graph B. I'll tell you in a second what exact cover means. So this function checks if it describes an exact cover in this graph, and if it does, then this function just outputs the bit P and bottom otherwise. Okay? So just a very simple function. Now you can imagine a program that does that. You can write a program that checks if T describes an exact cover in this graph and outputs the bit B if it does and bottom otherwise. And note that the only thing that I'm trying to hide for this function is this bit P. The graph G is public, everything else is public. The only bit we're trying to hide is the bit P. Let me tell you now what exact cover is, so the problem statement will be complete. An exact cover in this bipartite graph consisting of sets S and X, with S consisting of vertices A to F, and X consisting of vertices 1 to 7 respectively, is described by a selection or a subset of the vertices in the set S, such that each vertex in set X is connected with exactly one vertex in the selection. Okay? So what I'm saying is that the vertices B, D, and F describe an exact cover for this graph G. And what does that mean? That means that for each vertex in this set X, there is exactly one vertex that in the selection that's connected to. So if you were to look at vertex 1, it's connected with two vertices, A and B. But in the selection of B, D, and F, it's connected with only one, which is the vertex B. Similarly, the vertex 4 is connected with vertices A, B, and C, but in the selection, it's only connected with B, and so on. 2 points to keep here in mind is that actually exact cover turns out to be NP complete. So having the graph G there and is not sacrosanct. You could have an arbitrary NP relationship and reduce it to exact cover. Okay? The second point I want to make is, just like I made for witness encryption, is that when I'm going to be obfuscating this, this function or a program that implements this function, then that obfuscator doesn't even know whether this graph has an exact cover or not. Okay? So this graph, if has an exact cover, then this function should output the bit P once you provide it to it, and bottom otherwise. So this might seem like a much simpler primitive than the goal of obfuscating all programs, but this is something that was already open for several decades. So let's see, before we obfuscate this function, what does it mean to obfuscate this function or a program? Well, if you give me an exact cover and I've given you an obfuscation of this program, then you should be able to recover the bit P. That's functionality. But if you don't know the exact cover, then you shouldn't be able to recover bit P. Simple as that. It turns out to be rather tricky, but for the talk, I'm going to relax the security requirement and argue a weaker security property, which says that as long as there's no exact cover in this graph, the bit B should remain hidden. Okay? So if there's no exact cover, then there's no input on which the function outputs the bit B. At least in that case, it should remain hidden. And the fact that this problem is still non-trivial because the obfuscator doesn't know at the time of obfuscating this program whether the graph has an exact cover or not. So let's see how we're going to obfuscate this function. And recall the two-step approach where I was going to sort of convert this program, or in my special case, this graph, into a bunch of unencrypted jigsaw puzzle pieces, which I want to then encrypt using this new encryption scheme that we've developed. I'm going to start by talking a little about the encryption scheme that we've developed, and then we'll see how this scheme, or this new encryption scheme, enables construction of these encrypted jigsaw puzzle pieces, which come together to reveal the output on legitimate input combinations. So the encryption scheme is, I'm not going to go into the number theoretic details of how it's constructed, but just abstractly what it is. And abstractly, it's actually very simple. We're going to have an n-level encryption scheme. What the level means will become clear in a second. And the plain text space for this encryption scheme is ZP for some large prime P. Okay? So you're trying to encrypt all integers modulo some large prime P, and you could encrypt at n levels. What the levels indicate will become clear in a second. This encryption scheme, I'm going to require it to have some special properties. The first is sort of a very natural, I want to think of it as the intuitive idea that you come, that if I encrypt X at any level, the subscript here denotes the level of the encryption, actually hides the value that you're encrypting. Just a very natural property. The second property I'm going to require is that, and it's also going to implicitly define what levels mean, is that if I was to take two encryptions, an encryption of X and Y at levels I and J respectively, and multiply them, then this should yield an encryption of the product of the plain text at the level which is equal to the sum of the levels they were at. So if you take encryption of X at level I and multiply it with encryption of Y at J, you get encryption of XY at level I plus J. And you can keep doing it as long as the levels are less than n. So you cannot go above the level n. And this sort of defines what the levels are. So in particular, if you were to multiply an encryption from the first level and encryption of the second level, you'll get an encryption at the third level, which will correspond to the product of the numbers multiplied. The third property, which is sort of the new property in our encryption scheme, is this equality test property. It's a simple-looking property, and this is what is key in enabling both witness encryption as well as general obfuscation, is this, that if I give you two ciphertexts, encryptions of x and y, at the nth level, then you can check efficiently whether x is equal to y. Okay? So this is the new property that our encryption scheme has, which will enable the construction of obfuscation here. So let's see how this sort of encryption procedure can enable us in converting a graph into a bunch of encrypted jigsaw puzzle pieces, which enables computation of that secret bit B if you have the exact cover in hand. Okay? So here's our graph. I'm going to now describe the obfuscation procedure. Keep in mind that the obfuscation procedure has to be completely oblivious of the fact whether the graph has an exact cover or not. Okay? What I'm going to do is I'm going to start by picking a random numbers from the space ZP, one corresponding to each vertex in the set X. So I have A1 corresponding to the vertex 1, A2 corresponding to vertex 2, A3 corresponding to, and so on. Okay? So they are all sampled randomly from ZP. Now I'll describe what the obfuscation looked like, and it's going to consist of those encrypted jigsaw puzzle pieces. Let's see how those pieces are generated in this setting. I'm going to generate a 7-level encryption scheme. Okay? So the one I just described with n set to 7. And I'm describing the actual obfuscation, the obfuscated program, or the encrypted jigsaw puzzle pieces. So for corresponding to each vertex in the set S, I'm going to generate one ciphertext. So for example, if I look at the vertex A, it is connected with vertex 1, 4, and 7. I'm going to collect the random numbers corresponding to these three vertices, which are A1, A4, A7, multiply them, and encrypt the value at the third level, where 3 represents the degree of this vertex. Similarly, I'm going to generate a second ciphertext corresponding to the vertex B, and so on. Right? So note that so far I don't even know whether this graph has exact cover or not. All these sort of ciphertexts or encrypted jigsaw puzzle pieces are being generated oblivious of the fact whether the graph has exact cover or not. I hadn't embedded the bit B so far, and the bit B is going to be embedded in the 7th encrypted jigsaw puzzle piece and the final piece here. And I'm going to generate E as follows. If the bit B is 0, I generate the E as encryption of the product of A1 to A7 at the 7th level. And if the bit B is 1, then I generate the encryption just as an encryption of a random number from ZP. Okay? So these are my sort of encrypted jigsaw puzzle pieces. Let's see, if I give you an exact cover, how could you use these pieces to recover the bit B? And sort of fairly natural. As described before, this graph, an exact cover in this graph is described by these vertices B, D, and F. What I'm going to do is I'm going to look at the ciphertext or the encrypted pieces corresponding to these vertices. And well, what can I do with them? I can multiply them. If I multiplied them, what do I get? Well, I get an encryption of the product of the plaintext, which in this case corresponds to the product of A1 to A7. Note that the exact cover exactly specifies that there's going to be no repetitions of the random numbers here. So if I multiply, I'll always get an encryption of the product of A1 to A7, and at the 7th level, right, which denotes the size of or the number of vertices in the set X. Okay? So given this exact cover, I have access to this encryption of the product of A1 to A7, and now I also have access to, I also have access to an equality test, right? If I have access to this encryption of the product of A1 to A7, I can check if E and the product here are encryption of the same value or not. Okay? So if they're the same, then I know it's the bit 0. If they're different, then I know it's bit B is 1. Okay? So having access to the exact cover in the graph, I could put these pieces together, which in mathematical sense meant multiplying them together and checking if the product was corresponded to a certain value, and see if they and recover the bit B that way. The security property that we want is that if the graph has no exact cover, then the bit B should remain hid. Okay? So what I'm going to do is I'm going to remove this green edge in the graph that goes from vertex B to 4. And the removal of this edge is going to remove any exact covers in this graph. You can check. You don't have to. I went through all the cases, and it doesn't have any exact covers. But if you want, you can go through them. So I'm going to remove this edge. And note what is the difference in the obfuscation that it has. Instead of having, the only thing that's going to change is the ciphertext EB. So instead of having an encryption of the product of A1 and A4 at the second level, I'll just have an encryption of A1 at the first level. So now just by the very fact that this graph does not have an exact cover, there is no combination of the pieces from A1 to EA to EF, which can be multiplied together to obtain the product of A1 to A7 at the 7th level. And this sort of naturally implies the security property here. Okay? Any questions? Okay. Okay. Yes.
If I ask a question on your obfuscated program, I don't get bottom. I get B equals 1 as a response.
So it's actually easy to check. Sorry, I should have mentioned that. It's given an input. It's easy to check if on that input the program will output the bit B or bottom, because you can check whether it describes an exact cover in the graph yourself. You can check that yourself, right? So you just don't know what the bit B is. If you tell me that this is an exact cover, I can check myself whether it describes an exact cover. If it doesn't, then I'll just bottom myself, that I can do on my own. If it does describe, then I can use this methodology to recover the bit B. Right? Okay. So let me move on to the sort of the third part of the talk. We're going to talk a little about the kinds of problems I want to work on in the future. So my interests in cryptography are actually fairly broad, but for the purposes of this talk, I want to focus on the problems I'm interested in the context of obfuscation. And within that, I think that there's a lot of space both for work on the foundational crypto side and as well as on making crypto practical. So let me tell you about some of the examples of problems that are open in here. So sort of the first very natural problem is that what are sort of the minimalistic computational assumptions that are necessary for doing obfuscation. So everything in cryptography needs computational assumptions. And with respect to obfuscation, we have construction under certain computational assumptions. But what are sort of the minimal assumptions that are necessary? And we don't have any results on the negative side either. So it would be really interesting to have results which say that, look, you cannot base it on these assumptions, and these assumptions are essential, or improve on the assumptions and base it on more standard assumptions than the ones that we have. But I think an equally pressing problem is to make the constructions that we have more efficient. And I think that this is not just a matter of optimizing on the constructions or having more optimized implementations of our construction, but I think that new mathematical tools need to be developed if we were to get more efficient solutions here. And I believe that multiple breakthroughs will be needed to make that happen. But I think that this, this overarching goal of having obfuscation for all programs is a very, making that efficient is a very ambitious goal. And there are small steps that we can take towards that goal, which might be easier to achieve. And that, I think, is the goal of obfuscating special functions. Okay? So let me give you some examples of the functions which might be much easier to obfuscate than obfuscating all programs, and where more efficient solutions might be plausible. Think about AVG. It's an antivirus software. It's a free one that comes online. Now, what it does, how it works, is it has a database of virus definitions. And anytime it gets a program as input, it matches to see if the program matches any of the signatures that it has in its antivirus database. Now, what having this database as part of the software does is that an attacker who has access to this database could use this database itself to construct new viruses which will not be detected by the software. And so this is a clear problem that exists in how antiviruses are out there today. And one natural question is, can we have a mechanism to not have this database in the clear form, but in sort of an encrypted form or an obfuscated form where you could still match whether a program that's given to the antivirus and check if it matches one of the signatures that are out there, but without actually revealing the entire set to the attackers. So this is a much simpler problem where there's potential for more efficient solutions. Another example that I want to talk about is actually going back to something that I started with. What's really surprising is that right now the obfuscation solution is extremely inefficient, but if I were to use it to convert a private key encryption scheme to a public key one, then the only thing it affects is sort of the public key and the encryption time. It doesn't affect the ciphertext size or the decryption time. And what's amazing about this really simple solution is that it actually gives you a public key encryption scheme that beats every other scheme that's out there in the literature in terms of the ciphertext size and the decryption time. It's completely impractical because public size is enormous, and just for that reason you wouldn't use it. But the fact that you have such tiny ciphertext and such fast decryption time makes it a good direction to explore, in the sense that if you could just make obfuscation for this specific task more efficient, then it would give you solutions which might be able to compete with the best public key encryption schemes out there. Another direction I think which is very interesting is to use trusted hardware in making obfuscation more efficient. So a big chunk of the inefficiency comes from this new number theoretic tools that we have, multilinear maps, or the new encryption scheme that I call. It's very inefficient, and it brings in a lot of the inefficiency to the construction. It's possible to remove that and use sort of trusted hardware to build upon these and realize these solutions, avoiding that inefficiency that results from the number theoretic tools out there. Okay? So this is some directions where there's possibility for better efficiency in the near future. And there's also a lot of other applications, but I won't talk about that. So just to summarize, prior to our work, rampant use of obfuscation was in practice was commonplace, and the techniques out there were pretty ad hoc and sadly also insecure. And we sort of have the first theoretically sound software obfuscation solution, and it has helped resolve many problems in cryptography. Finally, I'd like to thank for NSF, IARPA, and DARPA for supporting my research at different points of my career. Thank you.
Thank you. Questions?
Yes. Do you have any idea about what types of programs you can and can't obfuscate? So for example, if I knew that the function you were trying to obfuscate was a constant function, you could try as hard as you want to obfuscate it, but all I would need is one sample of the input or the output to infer what the program is. Is there any kind of results on that?
So the question is that there exist these classes of functions, such as a constant function, which is easily learnable, and what does it even mean to obfuscate that function? So it's a great question, but the goal here is not to hide what can be learned from the input-output behavior. If the function is obfuscatable, then we don't say it's hard to obfuscate. In my wording, it's trivially obfuscatable. I can just give you the function. Any other obfuscation, from that you could have already learned the obfuscation, like what the function did on your own, because you could look at its input-output behavior. So the goal here is to prevent anything that you can learn besides the input-output behavior. Whatever you can learn from the input-output behavior is not something that we're trying to prevent. That's a part of the functionality. We want to enable that.
Let's thank the speaker again. Thanks.